4.4, it's about radioactive materials, unstable nuclei, reactive decay. So this explains, so there's two kinds of things. There's two kinds of reactions, chemical reactions and nuclear reactions. So far we look at just chemical reactions. And that involves an exchange of electrons. So in normal chemical reactions, all you see happening is atoms rearranging and moving around electrons. And that's what we see in the bottom picture. You see there's 4 gold atoms, 8 purple atoms, and they move around, they bond to each other. There's an exchange of electrons that keeps them together. So when they bond, the purple and orange atoms exchange electrons to create that bond. That's a chemical reaction. So no atoms are lost or gained, created or destroyed in chemical reactions. The identity of the atoms remains the same. So if you start with 4 hydrogens and 8 oxygens, you end with 4 hydrogens, 8 oxygens in a chemical reaction.
Did it change, like, did the number change if it was a physical reaction?
Physical, no. So physical reactions are just basically mixing. Like you basically, you put sand and salt, just mix up the sand and salt. The salt and the sand don't react at all, right? They just stay where they are. So that would be a physical thing where you only have them next to each other, but they're not reacting at all. There's no change in anything. Yes.
That'd be a homogeneous or
Well, it depends if it's evenly mixed. Now, if it's sand and salt, I mean, you have,
just kind of started with the spoon.
I mean, it'd be more homogeneous after you've done that, but it still wouldn't be really fully homogeneous. A solution is fully homogeneous. So like, like tea, coffee, that's homogeneous. You don't see the individual caffeine and sugar particles in coffee. So think about things like that. That'd be more. So if you can see the individual sand grains, it's not fully homogeneous.
Is that how it's pronounced?
Well, you can pronounce it either way. I mean, homogeneous, homogeneous. I mean, it really, a lot of words you're going to have 2 pronunciations or more that are correct. And you can really say it either way and be correct. So it really, either one is fine. I kind of go in between the two. I mean, I usually say homogeneous, but if I'm talking about it in class, I usually say homogeneous to just to, differentiate between homo and heterogeneous mixtures. But you can say it either way.
What's the second pronunciation of heterogeneous?
There isn't one. It's just heterogeneous. I mean, I guess you could say heterogeneous, but nobody ever says that. So it's just heterogeneous.
Do you need to have a picture?
No, I mean, it might help you if you do, but I'm not gonna require you to draw the picture.
So H2O2, what does that mean?
That's hydrogen peroxide. That's in rocket fuel.
Oh.
Very unstable, very explosive. Now, of course, we can use it in, if you can buy at the store, it's 3% hydrogen peroxide, but the rest is water, so it's very
Is that
dilute.
explosive?
No, 3% is fine.
Is it like?
Is it 30%?
Flammable, not 3%. Now, if it's, 30%, yes, or higher, but no, 3%.
What do they
It's
use
mostly
in
water.
rockets? Do they
Do you wanna?
use pure? Do they use pure H2O2?
I don't know if it's pure. I don't know if you can get that pure.
Wouldn't that be the most economic? Like,
Well,
you could
but the
fill
thing
them
is
with-
though, it's very unstable.
you fill the most
And I don't
space.
know how stable you can, I don't think you can make it that pure to keep it that, I don't know. I don't know. I think 70% is the limit you usually get for that.
Would it be possible to use nuclear energy in rockets?
Oh, sure, definitely. They already have nuclear submarines, so they could definitely also have nuclear rockets.
And nuclear ships, right?
Mhm. So they can definitely do that. I'm sure in the future they will. So that was a chemical reaction, but nuclear reactions we'll talk about in section 4.4 today. And they're a little bit different. So nuclear reactions, they actually change an element into a different element. So this involves a change in the atom's identity. This could involve splitting atoms into smaller atoms, or it could be creating larger atoms. Radioactivity is the name of the emission of radiation from an atom. So atoms emit particles and energy, and that's called radioactivity when they do that. Oh, and a notebook check. So I need to check if your notebooks this test. And it's a test grade for all the notes that you know, so make sure if you missed a day that you do get notes for somebody else. Number, you haven't been here for a while, so you don't have to worry about, you know, the ones you haven't been here for, just the ones you were here for. But for everybody else, just make sure if you have missed days, so you copy notes from somebody, and that you have all the notes for this quarter in your notebook, and make sure it's in order, and make sure it's neat before your test.
Just for this day?
Yeah.
So,
It's a quarter grade. I take it up every quarter.
so which chapters do we have to have?
I believe that's 3 and 4.
Thank you.
Wait, so just 3 and 4?
I believe so.
Why not 1 and 2?
Well, I do it every quarter. It's
Did
just,
you do it last quarter?
No.
I don't
You didn't do
remember.
it last
Did I
quarter.
not?
Yeah, we didn't try to remember.
We haven't had a single notebook check.
I think I just put in hundreds for you all, just assumed you're taking notes.
Thank you.
Because I always put a grade in for notes. But this quarter, I'll make sure to grade it for you all. So this coming test on Friday, make sure you have your notebooks. And again, if you miss days, make sure you copy notes from somebody.
So just chapter 3 and 4 for this one?
Let me see exactly when we started the second quarter. Yeah, it looks like we stopped, yeah, chapter 2 looks like that's when we ended quarter 1. So yeah, 3 and 4 for quarter 2.
So if there are any unstable elements nearby to a nuclear reaction, could it also explode those?
Yes,
Instead of just the uranium inside the bomb?
oh, for sure. Yeah, definitely it can.
How come it gives 2 different like definitions of nuclear reaction? Or is this just like?
It's just another way to think of it. And so when you change the atom's nucleus, you do change the identity of the atom. Well, you usually do. You don't always. But if you change the number of protons, it's a different atom at that point.
So chemical and physical don't change like the element at all, but the nuclear reaction does?
They change the identity of the atom, yes. So one example of a nuclear reaction you can see on here, uranium is hit by a neutron. That's what the 10N represents, is a neutron. It hits the nucleus and it makes the atom split. And that's how splitting the atom looks. And it involves the products of 2 atoms. You have krypton on top, barium on the bottom, with a lot of energy released, and then a few neutrons. 3 neutrons are released.
Why would it change it into 2 different elements?
It's just that when the atom splits, when you have different numbers of protons in the nucleus, you have different atoms. So it originally started with 92 protons. Uranium has 92 protons.
Why
But-
couldn't it divide into 46 and 46?
It could have, it's just that this is more stable. So to be stable, atoms have to have a good ratio of protons to neutrons. And splitting it this way gives them a good ratio of protons to neutrons for both. So it's the most stable way to split the atom in this example. So we have krypton on top with 36 protons, barium on the bottom with 56 protons. And that's the result of this nuclear reaction. So it's a very common reaction in atomic bombs to have uranium split into these atoms. So uranium-235,
So 235 is the neutrons, right?
235 is the number of protons and neutrons together.
Oh. And 92 is the electrons?
No, well, yes, electrons too. No, 92 is the number of protons and electrons. So it has 92 protons and 92 electrons.
And
Wait, that's-
235 is neutrons and protons.
Yes,
So the uranium 235, that's what they use for nuclear bombs.
yes. Mhm. Unstable nuclei lose energy by emitting radiation in a process called radioactive decay. And so elements naturally on their own will emit radiation. And as they lose energy, as they lose matter, that's called decay. radioactive decay is the loss of energy and the loss of matter. Atoms will undergo radioactive decay until they become stable. So atoms can be unstable if they have the wrong amount of protons versus neutrons. They have to have the right ratio of those two. If they have too many or too few, they'll try to emit energy in protons or neutrons to become stable. Yes.
Can nuclear bombs potentially happen by themselves?
No, you would have to have a lot of unstable elements all at one place for that to happen.
One unstable element couldn't just start the chain reaction.
You'd have to have a lot of other ones around it that are also unstable, or the ones that could become unstable. So you would need to have a lot of material that could potentially become radioactive and unstable around it. So you got a lot of uranium in one place and you bombard it with neutrons, then yeah, that could happen. You need to have a lot of energy, and you also need to have a lot of material that could become radioactive in that one place. And that's pretty hard to do that. Nuclear bombs start with an explosion. Like you start with a small explosion, which then creates a nuclear explosion.
So how do you make one unstable?
How do you make one unstable? You bombard it with neutrons and usually with neutrons, and that can make it unstable and split.
So then to actually make it like explode, it doesn't have to, like you said, by an explosion?
Yeah, you make a small explosion.
Would that be it, like hitting the ground or what?
Well, an actual bomb. So a nuclear bomb actually has a smaller chemical bomb, which explodes first. And that small explosion creates a much larger explosion.
And how do you control that to where it just like blow up?
Control it where?
Huh?
What do you mean?
How would you like control like the bomb from just exploding whenever?
Oh, well, you have to detonate the bomb. You have to actually make it, you have to light the fuse and make that small explosion happen first. And that small explosion then makes a larger nuclear explosion. It's kind of like a match. You have to light the match, right? I mean, the matches could light on fire. The whole box could light on fire, but you have to light that one match to make that happen, right? That's the same thing with nuclear explosion.
So they're somewhat safe.
Well, yeah, I mean, unless you, exactly, they are safe unless you light on
with
fire.
reasonable precaution, nuclear bombs are fairly safe.
Yeah, I know if you drop from a really high height, like if you drop from like the sky and it hit the ground, I mean, that might possibly explode. But unless you have a lot of force acting on it, it's not going to really do anything. Now, other things like TNT, that's very dangerous. That can explode any second. You know, like nitroglycerin and dynamite. I mean, that is very unstable, and that's not nuclear, but that's an explosive that can detonate just by dropping it from a very small height.
Like if you're carrying it and you drop
Yeah,
it.
that could definitely, or it can explode in your backpack, even just like by walking. And so it can be very dangerous. Now, of course, they made it safer over the years, but that's, yeah, nitroglycerin is very unstable.
How do they make it safer? Do they add other elements?
I believe so. I'm not sure exactly what they do, but I believe they do just make it more insulated, and so it's not going to be more prone to, you know, humidity changes, set off dust particles, set off friction. So they just make it more insulated, and that can help protect it.
Yeah, I'm gonna have that song, Glycerin stuck in my head all
Wait, which is that?
by Bush.
Oh, yeah. I'm surprised you know that one. So that's good.
Cultured.
Yeah, I'm impressed. Yeah, that's an old one. Kinsey would be proud.
My dad was
Oh, your dad. I was thinking your dad
proud.
too.
No, Kenzie would also. I don't know. Actually, I don't know if Kenzie listened to that type of like.
Really? I thought
I
she
mean,
did.
she knows them, but
Oh,
not,
okay.
like, she's more into like. I don't know.
You just
I mean,
try to
it is-
catch
it is
in every
rock,
single
though, like-
conversation,
But
huh?
it's like,
That isn't it like. I don't know. She's just more to like metal.
Oh, yeah, that's true. Yeah.
Wait,
As much as I want to know what Kenzie likes.
so it says if you lose 2 protons and neutrons, the atomic number decreases.
Oh, yeah, we'll get to that a little bit later. I didn't want to get to that exactly yet, but we'll get to that in more detail as we go on.
What's the last note?
What now?
The last note.
The last note?
Yeah. The one before, after this one.
This one?
After.
That one?
No, it was alpha,
Like
after
the-
alpha radiation, the next part,
Yes.
alpha, yeah.
Okay, alpha radiation. Emission of alpha particles. So there's, as you can see in this diagram, there's three kinds of radiation types. We'll go through them today. So alpha particles is the first one we'll talk about. So alpha radiation just is a name for emission of alpha particles. An alpha particle contains 2 protons and 2 neutrons. If you compare a table and look up what element has 2 protons, that's helium. So basically an alpha particle is helium. Because if you have 2 protons, that's what you have is helium. It also contains 2 neutrons.
Wait, the alpha particles are just helium?
They are. Now they're charged helium, so it's not neutral helium. But basically that's what, if you have 2 protons, you have helium.
So alpha particles are helium with extra electrons?
No, what they have no electrons.
Oh,
They just have 2 protons and 2, so they have 2 fewer electrons than other helium atoms do. Does everybody have these down? Okay. On this slide, write down just the bottom bullet point that it has a +2 charge. And so it has 2 protons, and each proton has a +1 charge, but there's no electrons to balance out the +2 charge. And so it just stays as +2. And that's why, now helium is neutral, but if you take away the 2 electrons, it becomes +2. And so an alpha particle is a +2 charge.
isn't helium super explosive?
No, helium's not, hydrogen is. But helium is very stable. That's why we use helium in balloons, because it's not explosive at all. You put a match to helium, it goes out right away. Now the Hindenburg blimp though used hydrogen because it's lighter than helium. But then it exploded and people died on that. It's really awful. And so after that, they stopped using helium for balloons because they realized how dangerous, hydrogen for balloons, because they realized how dangerous hydrogen was. Now they use helium.
So can they still make a blimp using helium?
Well, you can, it's just very dangerous. So
Using
No, helium.
Hydrogen.
Oh, helium, yeah, you can. Yeah, it's just,
Is
it's,
it light enough or no?
no, it's light enough. Yeah, you
Then
can,
why do they use hydrogen?
it's lighter and it's not, it's,
But if they knew it could go up in flames,
I don't think they realized the risk of it. I mean, they knew it could, but they didn't think it was gonna happen. I don't think they realized the full potential
How
of,
did it explode?
there's a small electrical spark, they're like a small spark of electricity. Static electricity, it could be,
did they know why
light.
it exploded?
I don't think they, I don't know if they do.
I thought they thought it was from one of the engines.
That makes
Yeah.
sense. I mean, engines create sparks all the time.
Yeah.
You know, so that might, I mean, it could be any little spark. So as I mentioned, this is equivalent to a helium-4 nucleus. And then you have 2 protons, 2 neutrons. That's the same thing as helium. There are other ways to write alpha particles as a symbol. So I want you to write down this symbol right here, just to know one way to write an alpha particle would be the alpha symbol, which is just an A basically, with 2 curls in the end. And then you have 4 in the top, 2 in the bottom. 2 represents number of protons, and then 4 in the top represents number of protons and neutrons together.
Wait, so what if the A looks like 2 curls?
Yeah, basically there's like, yeah, do you see there's small curls on either side of it?
Okay.
Like it's not like a straight line. Like normally for you draw a straight line and then circle, but this is more like a curl on the ends.
So the bottom number is the number of protons
Yes.
and typically the number of electrons.
Yeah, for a neutral atom, yes.
But in this
Yeah, this
case,
is
no.
not a neutral atom, and so that's not the
Oh.
case.
So how would you know it wasn't a neutral atom?
You have to be told.
Oh.
Wait, so 4 is representing what?
That's the mass number. That's how many protons and neutrons together that it has.
And the 2.
The 2 is how many protons there are.
How many what?
Protons. The other part on here, like the AZX part, I wouldn't even worry about writing that down. I'm not going to get to that, but we'll talk about another example in the next slide. But not worth getting into that.
Wait, I'm kind of confused about
So 2 is the number of protons, you
Yes.
said, and 4,
That's the mass number. That's how many protons and neutrons together that it has.
is that an alpha particle?
Yes. Let's go to this example now. And so what do we see happening here? We have radium to start with, radium 226. So the top number, 226, that's the mass number of radium. That's how many protons and neutrons it has. 88. That's how many protons that there are. Now what happens? Radium turns into radon when it loses 2 protons. It goes from 88 to 86. And so it's lost 2 protons when it's done that.
And it also lost 4 neutrons.
Very good. It lost also neutrons, right? Because what's the top number? It went from 226 to 222. So it had a loss of 4 on top. What does that tell you? Well, if you already lost 2 protons, you have to have lost
2 neutrons.
exactly, right? And so that tells you that it lost 2 protons and 2 neutrons.
But it kept the same number of electrons.
That's exactly
So
right.
it found the radon and the particle in both charged.
Mhm,
Wait, did
good.
it lose 4 neutrons on top or 2?
No, it didn't lose 4 neutrons. So the top number tells you how many neutrons and protons together that it has. The bottom number tells you how many protons there are, right? And so if it lost 2 protons, but the top number went from 4 different, it must have also lost 2 neutrons. 2 plus 2 gives you 4, right?
Why would they need to give you the bottom number if you just, like if it's equal, the protons? and neutrons?
Yeah, you wouldn't have to. That's true. I mean, you know that it would have to be. But it's not always. Sometimes you do have charged particles that don't have the same number of electrons and protons. But at normal normal neutral atoms, that would be true.
Wait, so protons and neutrons usually are equal?
No, not protons and neutrons.
Protons not.
Yeah.
Okay.
Okay, so that's an example of a nuclear reaction. That's alpha decay. And there's another example of what that would look like. Uranium undergoes alpha decay too. So uranium 235 goes from 235 to 231. The bottom number, 92, goes to 90. It goes from uranium to thorium. And then you have helium. Notice too that these numbers add up. So 90 plus 92, or sorry, 90 plus 2 gives you 92. 231 plus 4 gives you 235. So numbers both add up. The number of protons and neutrons is constant on both sides. Now they change, they move from the nucleus outward, but you can't destroy protons and neutrons. So the numbers will add up again. So that's one thing to keep in mind for these nuclear reactions is that the numbers do combine to equal the same on both sides.
I thought mass was lost in the nuclear
A
reaction.
little bit of mass can be lost sometimes. We'll talk about what happens later. But what you should keep in mind for right now is that the numbers are going to add up on both sides to be the same. We'll talk more about how mass is lost a little bit later. So nuclear equation shows atomic numbers and mass numbers of the particles involved. And we can see that they do equal each other on both sides. So the mass number is conserved. Number of protons and neutrons does remain constant. So we get different kinds of atoms. Uranium turns into thorium, and you also get helium produced. So we get different identities of atoms, but the amount of protons and neutrons adds up on both sides to be equal. And again, uranium does this because it's unstable as uranium-235. It becomes more stable when it loses protons and neutrons. Let's go into beta radiation. One thing also to keep in mind about this chart is that it shows you the 3 kinds of radiation types. Look at alpha so far. It's the purple one. Notice how it curves downward. It's going towards the
Positively.
negative plate, right?
So-
Opposites attract.
So it has
So
to be-
positive attracts negative. Did everybody get the notes down from the last slide?
Yeah.
Show me this down.
Wait, was the first one nuclear equation, was that already shown or is that?
I think it was already shown. I believe.
Yeah.
And then the top one, beta, that's the blue line. So beta curves upward towards a positive plate. So beta has a negative charge, negative attracts positive, and that's why it moves upward. So beta radiation is the emission of beta particles. And a beta particle basically is an electron. You know your question?
Why does it curve upwards more if it has less charge?
Oh, that's a good question. It's
Because it
lighter.
curves Up a lot.
Yeah, that's a good question because it's lighter. Beta is a lot lighter. It's about 2,000 times, no, actually more than that. It's about, what would that be? 8,000 times lighter than an alpha particle.
Oh.
Because it's so much lighter, it can be pulled up more easily.
Oh, because electrons are a lot smaller,
Exactly.
and then alpha particles are like, what, 4?
Yeah, that's right, mass number 4, yeah. So electron is 0.0005, and the alpha particle is 4 atomic units. So it's very different mass. So beta particle basically just an electron that has left the nucleus. So everybody have these down? So this is an example of a beta radiation. So we have carbon 14 and it turns into nitrogen 14. So what's happening here? Do you see how it went from 6 to 7? So what has changed?
There's extra neutron.
Not an extra neutron. The bond number tells you how many protons there are, right? So it gained a proton.
Wouldn't it be an electron because there's 14?
Well, let's think about just about the protons first, and we'll talk about electrons a little bit. But you go from 6 to 7, right? That tells you how many protons there are, right? So what has happened? It must have has a new proton, right? Now, the neutron number stays constant, though, or actually the neutrons plus protons remains constant. So it still is 14 on top, right? So the total amount of protons and neutrons together is still 14. But what has happened? On this side, carbon 14, it has 6 protons. How many neutrons are there? No,
Eight.
right? 14 minus 6 is 8. So it has 8 neutrons and 6 protons. How about nitrogen 14?
7.
7 protons and 7 neutrons, right? So what has happened? We said that it gained a proton, and what happened to the neutron? We lost a neutron, right? So basically what happens here is a neutron turns into a proton and an electron. So a neutron splits into a proton and an electron. And that's what we see happen in beta decay. Let's go, I'll show you this really fast. We'll go back to the other slides. So in beta decay, we have a neutron in yellow splitting into a proton and an electron. So I mentioned this earlier, that neutrons weigh a little bit more than protons do. So they can split into an electron and a proton. So neutrons have no charge, but they can split into 2 charged particles. They can split into a +1 proton and a -1 electron. So beta decay turns neutrons into protons. So if the atom has too many protons, it's too unstable with too many protons, then beta decay can happen where it can convert the neutrons into protons. We can see the bottom equation. So a neutron has 0 protons, right? So we put a 0 down here because there's no protons for a neutron. The top number tells you how many neutrons and protons together there are. So we have 1 on the top for the neutron. Then the proton has 1 proton. And the top number is how many protons and neutrons together there is. So it's 1, 1 for the proton. The beta particle, we put a -1 down for that. because beta results in a loss of a proton. So that -1 represents the loss of a proton. So do you see how the numbers here also add up? We do 1 plus 0 to get 1 on top, 1 plus -1 to get 0. So this equation also works. And that represents the conversion of a neutron to a proton and an electron. And an electron we call a beta particle in this case. So a beta particle is an electron, but it's an electron that leaves and goes out. It goes to the nucleus and it leaves the nucleus. Electrons, we call them electrons that they stay orbiting around the nucleus. The beta particles are made in the nucleus, then they are ejected from the atom. And so that's the difference between electrons and beta particles.
So in alpha decay, 4 protons and neutrons.
Well, yeah, 2 protons and 2 neutrons, together makes it 4,
Yeah.
yeah.
Leave the nucleus, and in beta decay, 1 electron leaves the nucleus.
Exactly right, good.
So an
Yeah.
electron is called an electron if it stays within the
And
nucleus.
it's orbiting, and it's
becomes a
orbiting,
beta particle if it leaves the nucleus.
exactly.
So it's just an electron, basically.
It is, it's just the difference is that for beta particles, they move out of the atom, out into the atmosphere.
Wait, so are neutrons like made of protons and electrons?
They can be thought of that way, yes, because they can convert into those things. So yes, you could think of them that way. Let's go back to this now. We already wrote down the top 2 bullet points, so don't worry about writing those down unless you don't have those yet. But the equation, let's write that down. So beta decay equation, you can see uranium-235 can also undergo beta decay, where you see you go from 235, still 235 on the right-hand side, but goes from 92 to 93. So it gains a proton to convert from uranium to neptunium. And then it ejects an electron. So again, in this case, uranium's nucleus has too many neutrons, not enough protons. So the neutron converts into a proton and electron. The addition of a proton makes it go to neptunium, 93 protons now. And it ejects a beta particle from the nucleus. The electron it's made is ejected, emitted out of the atom into the atmosphere. And that's the beta decay that we can write as beta, as the italicized B, or we can write it like this, where it's just an electron. So either one we can write for the symbol. Do you all have the equation down? So you'll find for all these, you can write them in different ways. So some symbols you can write, the alpha symbol, or you can write as 4,2 helium. For beta, you can write as the beta symbol, or you can write as E for electron. They're both the same thing. So you can see right here, we can also write it like this, where it's just the beta symbol. So carbon-14 can also undergo beta decay, where it goes from carbon-14 to nitrogen-14. This one we already wrote down, didn't we? I know we went through this.
Yeah.
So, but just to show you, we can have the symbol like beta or as an E for electron. They're the same thing.
So basically, all beta radiation is gaining a
Proton.
losing a neutron, and gaining an electron.
Well, the electron actually is not gained because it's shot out
And
into
an
the
electron
atmosphere.
is just kind of dispersed.
Exactly. Yeah. Okay, I already talked about that. The last radiation type is gamma. That's the emission of gamma rays. We can see right here that gamma just goes straight through. There's no charge to gamma. It's not deflected by the plate, so we know it's not charged because it just goes straight through the metal plates. It's high energy radiation. It's the highest energy of all the particles. We talked about beta, alpha. It's pure energy. There's no mass to it. So it's not a true particle. It's just pure packet of energy. It's also neutral. There's no charge to it.
Oh, so it's just basically energy.
Hmm?
It's basically energy coming out.
It's pure energy, exactly right.
So what happens is alpha decay happens, and then beta decay, and then energy is created. from that.
Exactly. Good. That's right.
Do alpha and beta decay have to happen at the same time?
No, they can be separate. So you could have alpha and gamma happen at the same time and no beta. You could have alpha, beta and gamma happen. You could have all three happen.
But gamma radiation only happens when alpha or beta or both.
Generally, yes. Generally, gamma is tied into one of the other ones. It's usually not. It can happen on its own. It's just not as common. Usually, it's going to happen with other kinds of radiation. The symbol for gamma radiation, you can see that this is a Greek letter. Looks like a Y, and you can see 0, 0. So there's no protons, no neutrons. It has no mass to it. So we write the symbol as 0, 0, and then gamma is the Y symbol.
What is it? Basically a straight up line and then a
Basically, it's just a Y, just like a curly Y. So one kind of gamma decay that we can see. Now this is actually not a good example of it just because it's missing part of it. So we can see that in this equation right here, uranium-235 goes to thorium, which 231 on top. So we can see that it's lost lost 2 protons, 2 neutrons. So this is actually alpha decay. And so it should also show an alpha particle also being released. It doesn't show that in this picture, but it should.
How would it lose 2 protons because 92 stays the same?
Oh, I'm sorry.
Wouldn't that be just 4?
That's a mistake. Yeah, it should not be 92 down there
Oh.
because thorium should be 90. Yeah, so they just didn't write that down correctly. That should be 90 for thorium. So as I mentioned, usually it accompanies alpha and beta radiation. So this is the right equation I showed you in the last slide. This is what it really should look like. So you have uranium, 92 protons, loses 2 protons to become thorium 90. It also loses 2 neutrons. That's alpha decay. So it loses an alpha particle. And also it ejects some energy, which we call gamma radiation. That's usually how we see gamma radiation produced, is along with beta or alpha decay. This is another way to write out what we see. So we can write just the alpha particle as just the curly A, or we can write it as helium. They're both the same exact thing. Beta, sorry, not beta, gamma, we can write as just this Y symbol, or we can write it as 2 zeros with a Y.
So alpha and beta radiation happen because kind of like a ball falling towards Earth because of gravity, they happen because they want to.
Yeah, it becomes more stable, right? If you would just have, this notebook right here and I just drop it, why does it fall to the ground? Well, because it becomes more stable as it hits the ground. It's looking for more stability. Or if I have something like resting on an edge, right? It's becoming less and less stable. Eventually it's going to fall. It becomes more stable and hits the ground. So that's why that happens. It goes from high energy to low energy. It becomes more stable as it goes down to low energy.
And then gamma rays are the result of that, the protons and neutrons being changed about.
Exactly.
How would gamma radiation exist on its own?
If the atom has too much energy, it can be excited by giving it energy through electricity, through fire, through heat. You can give the atom too much energy and it can release energy in that way sometimes. It's just not as common, but that can happen. So I mentioned this, we just haven't written this down yet. The primary factor in determining the atom stability is the proton to neutron ratio. And that determines whether it's undergo alpha decay, beta decay, or just not undergo any decay and just stay as it is. So alpha decay happens when there's too many protons, when the proton to neutron ratio is too high. Oh, I'm sorry, I got that mixed up. Neutron to proton ratio is too high, or too low, sorry. Proton to neutron is too high, or neutron to proton is too low. Either way. What was your question, Emma? So let's look at just the neutron to proton ratio. So if you need more neutrons or need to get rid of protons, alpha decay happens. So alpha decay, you can see it starts as radon 88, and it goes to, starts at radium 88, and it goes to radon 86. So it goes from 88 to 86 protons. And it goes from 138 to 136. So 138 neutrons to 136 neutrons. So if you start with 138 neutrons over 88 protons, you get a ratio of 1.57. At the end with radon, you have 136 neutrons over 86 protons. That gives you a ratio of 1.58. And so we can see that now the neutron to proton ratio is getting a little bit higher. You have more neutrons per protons when you go from radium to radon. And so it gets more stable through alpha decay if there are too few neutrons or too many protons. And then beta decay just does the reverse. Does everybody have these done? So it depends upon the atom on what the right ratio is, but it varies a little bit slightly from atom to atom.
So it's kind of like a scale and they're trying to balance it out.
Exactly. So atoms that are too massive, basically what has to happen, there's glue. Well, it's like glue, it's not really glue. It's a force that sticks neutrons and protons together. But if you have an unbalanced amount of protons and neutrons, then the force cannot pull them together tightly enough and it becomes unstable. We already talked about that, so let's skip that. On this slide, just write down what beta decay does. This occurs when the neutron to proton ratio is too high, just the reverse for alpha. So we can see that you start with carbon right here. It goes to nitrogen. And we can look at the neutron to proton ratio for carbon. That's 8/6. That gives you a ratio of 1.33. It becomes nitrogen, 7/7. That's a ratio of 1. And so we can see how the ratio changes. So that's if we need more protons and we need to get rid of neutrons, then this happens.
So is carbon unstable?
It's slightly unstable, yeah. Carbon-14 is slightly unstable. So over time, carbon-14 will change into carbon-12 or nitrogen.
Is anything totally stable? Like,
I mean, the lighter atoms are generally more stable than heavier atoms. But yeah, most atoms will over time decay. I mean, most isotopes will decay over time.
are there noble gases the most stable?
Well, even they will decay too, but we're talking about isotopes though. So for carbon itself is very stable. It's not going to explode. But within the carbon sample, you have carbon-12, carbon-14. Carbon-14 will decay into carbon-12 or into nitrogen-14. But you still have a bunch of carbon in there. Within the sample, there's not many carbon-14. It's mostly carbon-12. So you don't have much that decays. Did we get those down?
Can carbon-14 be created by some other element?
Oh yeah, it's definitely possible. You can have a bigger element that can that can create carbon-14, but carbon-14 is not that stable, and so probably wouldn't create carbon-14. Probably would do carbon-12 instead.
What's the biggest known element that like nothing can create? Nothing can be be broken down to create that?
Well, I mean, generally, it's gonna make,
Would it just be the
I mean,
farthest right on the? period?
really, I mean, generally above 90, it's not gonna usually happen. Like usually like 90, 92, usually it's gonna be below that.
So could 117, whatever that's called, in the US, could that break down into almost anything?
Yeah, I mean,
Below-
again, there
below
are
90?
limits. Like it would not break down to like 102 because 102 is not very stable either.
But would it, like,
Um,
anything kind of below 90?
Yeah, it would bring into smaller, like generally anything below 92 and below.
Oh.
Because anything that's above about 90, 92 is pretty unstable. And it would break into more stable, smaller atoms.
Oh.
Just to give you another, just to give you another way to think about this radiation, like as far as human health goes. So alpha particles can be blocked by even very small paper, even very thin paper. So by clothing or by paper, you can block alpha radiation. We have alpha radiation right now in this classroom. The smoke detector right there is a Americium, which you can see in the periodic table. Oh, where is that? I just lost that one.
I think it's not.
It's 95 AM. So that one is going to break down and release alpha particles. But it's harmless to you because your clothing, your skin blocks it. Tomorrow we'll talk more about this. Tonight for homework, on page 124, do 25 through 29. On page 124, 25 to 29. Good day.
Do you want us to turn it on?
Oh, yeah, you can just keep it for tomorrow, but it might be easier to see after the bell ring.
So, Dan, Ollie, I forgot to give you a 1.0